Welcome. Here's what nobody tells intermediate C++ programmers. The manual memory management skills that got you this far are actually holding you back. In modern C++, you almost never write new and delete directly. Instead, you use RAII. Resource acquisition is initialization, and smart pointers. Think of smart pointers like a hotel keycard. When you check out, the room gets cleaned automatically. You don't have to remember to delete anything. The lifetime is managed for you. Let's learn how. This is the pattern you should recognize and replace. Widget star widget equals new widget. Then later, delete widget. This style is error-prone for 3 reasons. First, if an exception is thrown between the new and the delete never runs. You leak memory. Second, if you add an early return path, you might forget to delete. Third, if the code is complex, it's easy to lose track of who's responsible for calling delete. Every one of these scenarios is a real bug that happens in production code. Manual new and delete is how C++ earned its reputation for being dangerous. Modern C++ has better tools. The fix is simple. Auto widget equals std make unique of widget. Make unique allocates the widget on the heap and wraps it in a unique pointer. When the unique pointer goes out of scope, at the end of the function, when an exception is thrown on any return path, the widget is automatically destroyed. No explicit delete needed. The rule is, prefer stack allocation first. If an object can live as a local variable, that's the best option. If it truly needs dynamic lifetime because its size varies at runtime or it needs to outlive the current scope, use unique pointer. This is the normal modern path. Sometimes a single owner isn't enough. Multiple parts of the program need the same object to stay alive as long as any of them need it. That's where shared pointer comes in. Here, we create a config object with make shared. Then we pass it to a worker and a logger. Both hold their own shared pointer to the same config. The object stays alive as long as at least one shared pointer exists. When the last one is destroyed, the config is cleaned up automatically. But a warning, shared pointer should be your last resort, not your first. It introduces atomic reference counting overhead and can make ownership relationships unclear. Reach for it only when multiple owners truly need independent access. 3 tiers for managing object lifetime, in order of preference. First, stack objects, local variables with automatic lifetime. 0 overhead, deterministic destruction, impossible to leak. This should be your default. Second, unique pointer. For objects that need dynamic lifetime with exactly one owner. The owner destroys the object when it's done. Cheap, clear, and safe. Third, shared pointer. For objects with multiple independent owners. Reference counted, thread safe, but heavier and harder to reason about. Start at the top. Move down only when the simpler option genuinely doesn't work. Most programs need very few shared pointers. Unique pointer expresses single ownership, but ownership can be transferred. The function makeWidget creates a widget and returns it as a unique pointer. The caller receives ownership. The function install takes a unique pointer by value. This means the caller must std move the pointer in, explicitly giving up ownership. After the move, the caller's pointer is null. The callee now owns the widget. This pattern is clean, explicit, and self-documenting. The function signatures tell you exactly who owns what. Returning unique pointer means the factory gives you ownership. Taking unique pointer by value means the function takes ownership from you.
Shared pointers have a hidden danger.
Reference cycles. Imagine two node objects. Each holds a shared pointer to the other. Node A keeps node B alive. Node B keeps node A alive. Even after the rest of the program releases both, they keep each other alive forever. A memory leak. The fix is weak pointer. In this node struct, next is a shared pointer. It owns the forward reference. But prev is a weak pointer. It can observe the previous node without keeping it alive. When all shared pointers to a node are destroyed, the node is cleaned up, even if weak pointers still reference it. Use weak pointer for any back reference, parent pointer, or observer in a graph-like structure.
Here's the cycle problem
Made concrete. Two-person objects each hold a shared pointer called partner, pointing to each other. When the program releases its references to both persons, neither can be destroyed. Each is kept alive by the other's shared pointer. The reference count never reaches 0. Memory leak. The fix. Change partner from shared pointer to weak pointer. A weak pointer doesn't increment the reference count. It can observe the object, but it doesn't keep it alive. When the program releases its shared pointers, the reference counts drop to 0, and both persons are destroyed correctly. Weak pointer breaks the cycle.
Modern C++
Draws a clear line between owning types and borrowing types. Owning types manage lifetime, unique pointer, shared pointer, vector, string. When they're destroyed, the data is cleaned up. Borrowing types only observe. Span, string view, references, raw pointers. They provide access to data owned by someone else. The function draw takes a span of const pixel. It reads pixels but doesn't own them. The function greet takes a string view. It reads text but doesn't own it. This distinction is one of the most important modern C++ habits. Borrowing APIs are lightweight and powerful, but the caller must guarantee the source data stays alive for the duration of the call.
RAII
is what makes exception-safe code ordinary rather than special. Without RAII, you call new, then call a function, then call delete. If the function throws an exception, delete never runs. Memory leak. With RAII, you use makeUnique, then call the function. If it throws, the unique pointer's destructor runs automatically as the stack unwinds. The widget is cleaned up on every path: normal return, early return, or exception. This is the fundamental principle. Acquire resources into objects immediately and let destructors handle cleanup. RAII applies to everything: memory, files, locks, network connections. If the resource is owned by an object, it can't leak. 5 questions to ask about every resource in your program. 1. Can this object live on the stack? If yes, make it a local variable. Done. 2. If it must be dynamic, is there exactly one owner? Use unique pointer. 3. If multiple owners seem necessary, can you redesign to avoid shared ownership? Often, you can restructure so one object owns and others just observe. 4. If shared ownership is genuinely required, where could cycles appear? Identify back references and use weak pointer for them. 5. Are your APIs expressing ownership separately from borrowing? Functions that borrow should take references, spans, or string views. Functions that take ownership should take unique pointer by value. These 5 questions will guide you to the correct lifetime strategy every time.
Here's the key takeaway.
Smart pointers are like hotel key cards. When you check out, the room gets cleaned automatically. You don't call delete. The lifetime is managed for you. Stack objects for most things. Unique pointer for single ownership. Shared pointer only when truly needed. Weak pointer to break cycles. Views and references for borrowing. RAII for everything. For next topics, continue with STL containers and algorithms to learn the standard library's data structures and how to write expressive, efficient code with ranges and algorithms. Then, templates and generic programming to write code that works with any type. You now understand modern memory management. No more new and delete. Thank you.